welcome everybody to this conference entirely devoted to the concept of topos here at ihes, which is the place where toposes were originally introduced by Grothendieck in his Séminaire de géométrie algébrique du Bois-Marie. So the aim of this conference is to illustrate the wide-ranging impact of the notion of topos across different mathematical areas and encourage further developments in this direction. Grothendieck, in fact, was himself fully aware of the importance and the unifying nature of the concept of topos. In his text, Récoltes et mailles, he compares the notion of topos to a double bed, realizing an harmonious marriage between the continuous and the discrete, or also to a large and peaceful, very deep river in which all the king's horses could drink together. This explains our apparently eccentric poster. So this is what Grothendieck thought about the toposes. He looked at the toposes as unifying spaces, and more precisely, here is what he wrote. C'est le thème du topos qui est ce lit où cette rivière profonde où viennent s'épouser la géométrie et l'algèbre, la topologie et l'arithmétique, la logique mathématique et la théorie des catégories, le monde du continu et celui des structures discontinues ou discrètes. Il est ce que j'ai conçu de plus vaste pour saisir avec finesse, par un même langage riche en résonances géométriques, une essence commune à des situations des plus éloignées les unes des autres. For those of you who are not familiar with French, here is a translation. It is the theme of toposes, which is this bed or this deep river in which come to be married geometry and algebra, topology and arithmetic, mathematical logic and category theory, the world of the continuous and that of discontinuous or discrete structures. It is what I have conceived of most broad to perceive with fineness by the same language rich of geometric resonances, an essence which is common to situations most distant from each other. So we hope that this conference will stimulate more people across the different areas to study and apply toposes in their work, as Grothendieck himself had envisaged and hoped for. So I would like to thank all of you for coming here, so numerous, and in particular the speakers for accepting to give talks that promise to be very interesting. And of course, I would also like to thank the other organizers for joining me in this adventure. And of course, the IHES for hosting us, and also for the financial support, which was also given by the Fondation L'Oréal UNESCO pour les femmes et la science. And this is basically the funding that made it possible to organize this meeting. Thanks again, everybody, for being here. We hope that the conference is going to be enjoyable and fruitful. So now I guess that it's time for me to leave the word to the first speaker, Pierre Cartier, who will give an historic introduction to the concept of topos. Thank you again.
So I will give a historical account of the theory of sheaves. Sheaves came before topoi, and topoi is just a synthesis of all different kinds of sheaves. So I will start. Here are two Bibles, the book by Godemar, Théorie des faisceaux, and the Carton Seminar, the two Bibles, and I will refer to them later on. So the first part will be prehistory, or Riemann versus Weierstrass. So the problem which was tackled by both Riemann and Weierstrass in very different ways is a problem of multi-valued holomorphic functions. First of all, holomorphic functions can be defined as follows, which is Cauchy, Riemann, and I would like to add Diderot. D'Alembert. Equations. What we call the Riemann-Cauchy equations, which can be written as df over dz bar equals 0, were written explicitly by Cauchy and then by Riemann, but about 50 years before by D'Alembert in his study of the wind motion. And so the Cauchy-Riemann equation have an interpretation in fluid dynamics, and D'Alembert was studying the motion of wind at a global scale of the Earth, and discovered that he could use complex variables. Of course, the theory of complex variables were just in the preliminary form, but he could use, and so he could use, for instance, sine of x plus of iy, etc., as a function. So, but of course, it has been more or less forgotten for a long time, and it's only recently that good connection were discovered. So Cauchy-Riemann equation, so it's a kind, I will not write it more explicitly, it's a kind of differential equation, system of first order differential equation, if you replace f by its real part and imaginary part. And the idea is that, or in slightly modern form, you consider an open set U in the complex field, and you look for a function which is defined on U, f from U to C, and which is a solution of this differential equation. And as in modern slang, I mean, the collection of all these for all open sets form a sheaf in a modern form. And more generally, if you can replace this by an arbitrary linear differential equation, or even nonlinear differential equation, you can have the same situation. But the point of view, of course, the challenge is to study the multi-valued function. The most simple example of multi-valued function is log z. Of course, what is known is that, by definition, d log z is dz over z, which means that if you consider z as a real positive variable and you make an initial condition, log of 1 is 0, then you get a unique solution over the real axis. But soon it became important to study log for complex number. The first study was done by Euler, and Euler asked a question repeatedly, what is the value of log minus 1? Of course, if minus 1 to the square is plus 1, and if you use a functional equation, log of AB is log of A plus log of B, you conclude that log of minus 1 is 0. But if you want to be brave enough to try to consider log of z as a complex variable, you soon realize that, and Euler knew it perfectly, that when you approach, so if you remove the negative line, minus infinity to 0, the rest is simply connected, so C minus, which is to make a cut. This is simply connected, and the differential, from the general principle of differential equation, this differential equation, d log z is dz over z, has a unique solution, provided the normalization log 1 is 0, which is defined as this. But when you approach the two lips of this cut, you'd get different values. Well, if you approach minus 1 from above, you get pi I, from below minus pi I, and then there is a difference. So that was a challenge. And what is the true value of log z? If you don't make a cut, Similar problems occur when you want to solve not differential equations, very simple, primitive, but let's say if you want to calculate, to find what is the solution of y squared is x 1 minus x. Of course, if you consider a segment from 0 to 1, real segment to 1, you have two solutions. We differ by a sign. Choose one, let's say. Choose that y is square root of x 1 minus x for x between 0 and 1. Okay, now the problem is try to extend this for a complex number. How can you calculate the square root of a complex number? From a modern point of view, of course, if you make two cuts, if you remove now, the real line from minus infinity to 0 and 1 to plus infinity. The rest is simply connected, and it's a general principle that if you have a continuous function on a simply connected space, you can take the square root, but there are two branches, plus or minus. So, but if you want to have agreement over the real part, 0 to 1, you have only one solution. So you have a solution, you have again a complex solution of this equation. So when x is real and complex, provided it's not on the cuts, y is well defined, but you have two branches, plus or minus 1. But then, again, when you have the same problem, if you approach from the top or from the bottom the cuts, then you get different regions. If you start with one determination, let's say, and you approach it from the top, then you meet the other branch, minus 1, which comes from below. So that was a challenge. And and similar things occur for differential equation. The most conspicuous example is about the hypergeometric function f2 2f alpha, beta, gamma, z. I will not repeat. It's given by a certain power series in z, which converges, with radius of convergence is 1. So you have a function which is well defined on the unit disk. But then you want to extend it. And you have a certain differential equation. No need to write it in detail. But now, as Euler discovered and Kummer exploited, this function has an integral representation. And the integral representation is of the type 0 to 1 t alpha, well, alpha prime, 1 minus t beta prime, 1 minus tz gamma prime dt. Don't have, well, there are some relation between alpha, beta, gamma, and alpha prime, but it's not important. But the point is that if you consider this integral, and you consider that yes, then you can see it's well defined because it's a real integral over z1. But of course, the difficulty is about this. T alpha prime, okay. And then if you choose z, which is not on the cut from 1 to infinity, then you can choose a proper branch of 1 minus tz power gamma prime and integrate. And again, you have a solution which is defined outside of this cut. But it's a second order differential equation. And then you have two solutions, two linearly independent solutions. The other solution, I will not give the precise formula, the other solution appears to be holomorphic except on the cut minus infinity to 0. So in order to have all the solution, you make these two cuts. Again, you have if you make the two cuts, you have a simply connected domain, and according to general result, a second order linear differential equation has two linearly independent solutions. And so, but the same problem which was solved by Kummer, if you take one branch, that means one solution, and if you approach the cut from below or from above, because the differential equation remains valid, one solution will approach a linear combination of two. One solution from the top, two certain linear combination from the bottom. Which means that if you have a vector space V of S of solution, which is two-dimensional, then when you approach from the top of the top, that means if you make a full turnaround 0, you have a linear transformation, which is exactly what we call monodromy. But since there are two singular points for this differential equation, there are two monodromies, one around 1, one around 0. And they generate a certain group of linear transformation, which was given in explicit form by Kummer. So that's and now what do we do? Riemann, motivated by this example, introduced the idea of putting sheets and gluing them together. For instance, for the square root, you have two sheets. On one sheet, which is a copy of this simply connected domain. You take the branch of the function which is positive on this interval 0 to 1, and then then you put -1 on the other sheet. So you have two sheets, and in order to describe the connection rules, I mean the boundary connection, which brings one solution to the other one when you approach the cut, then you make a geometrical picture by taking two sheets of paper, cutting and pasting. Of course, this is highly intuitive, and it was advocated by Riemann, but the criticism came from Weierstrass, and it's also a political fight. The two major centers of mathematics in Germany at the time were Berlin and Heidelberg and Göttingen, and there was a bit of fight between the people in Göttingen, mostly around Felix Jahn and Hilbert, and in Berlin, mostly around Weierstrass. There was recently in Berlin a celebration of the 200th anniversary birthday of Weierstrass, and many good explanations were given at that occasion, and I was there. So now this is Riemann, which is quite intuitive. And it's not by chance that one of the books by Hilbert is called Anschauliche Geometrie, which is translated as Geometry in the Imagination, which is not a good translation. It's more geometry as you see it, Anschauliche Geometrie. Anschaulich in philosophy has a very strict sense, which is not the imagination. Okay, so then, but on the other hand, Weierstrass came with a different solution. His solution was the following. If you consider a function, holomorphic function, well, let's say a solution of the Cauchy-Riemann equation, around a given point z0, then you know that you can expand it as a power series sigma a n z minus z0 power n for n0 positive. Suppose that you have 2 points, z prime 1, z prime 0, and z double prime 0, and similar expansions, so I put a prime, and then coefficient in and a double prime n. Okay, you have two solutions, two power series expansion. For instance, they represent solution of algebraic or differential equation. How can you say that it is the same solution? How can you, which is a problem of analytic continuation. Of course, analytic continuation has a sound solution in the complex domain, but people now try to do holomorphic function in a p-adic. It is much more complicated, and it would require 3 hours to explain how to do it in the p-adic case. Okay, so now you have this solution, and then the proposal of Weierstrass, and that you trace a path from z prime 0 to z double prime 0, and you follow by continuity this power series. Well, more precisely, inside a circle of convergence, if you have another point, then you can transform this power series expansion into another one which is not centered at z0 but another point. And then you follow along the path, and you get a transformation which is analytic continuation. If you give me a path and you start with a power series expansion around the origin of the path, can you go until? Well, of course there may be obstacles, but you can assume that there are no obstacles. And if you have a differential equation or algebraic equation, only the singular point can prevent you from following. So now the proposal in slightly modernized form, is the following by Weierstrass. You consider the complex plane, and your running point is called z, and then you consider the following. You consider some power series, some a n t n, and positive. We call it phi of t. So a series corresponds to a collection of coefficients with some boundedness condition, with some gross condition, which give you that the radius of convergence is not 0. So now what you have, if you call S the set of all these series, you are really dealing with C times S. C times S. You give a point and a series. Now, analytic continuation can be as follows. If I give you a point z0 and a phi 0 and a phi 0, and that's what I explained, you consider the radius of convergence of this series. And if you try, and if you have a power series which is centered at z0, by transformation, which are made completely explicit by Abel, you can generate a family of a power series for this. And so it means that given a point in this space, you can have a neighborhood. And you take this as a neighbor. So in the product, C has the ordinary topology, and S has no topology at the moment. And then you can have disk, you can lift. If you start from this, you lift this small disk to this. And of course, it says that in the collection C times S, you have a collection of neighborhoods, and it generates a topology. It generates a topology, which is Choquet used that often in this lecture on analysis, this presentation, which is just a small variation. But then, now you have a topology on C times S, and now if you take this topology is disconnected, there are many components, and the Riemann surface is just a connected component of this. So it's a Riemann surface, call it R, is a connected component, but it has obviously a projection over C because it's part of this project space, and it has also C, which is Z, but also you can have another projection. You have another projection. Well, not a projection. This is projection, which I call it Z, and then you have f of Z, which is the function, corresponding to the Riemann surface. So a function, or homomorphic function in this setup, is not a function over an open set in the complex domain. You have first to consider a covering, which is, of course, étale covering, as we know now. And then the function is not defined on C, but it's defined on this. That's the idea of Riemann surface. Okay, so now it can be, we can make the connection between the two approaches, and in modern terms, it corresponds to consider a sheaf by its section over open set, or by its étale space, corresponding étale space. So, but this is a prehistory, and already all the ideas are there, and they were made quite explicit by Hermann Weyl in 1911 in his book, The Idea of Riemann Surface. Die Idee der Riemannschen Fläche. That is more philosophical. Okay, so that's the prehistory of shapes. Now, what comes next? Second is Le Ray, from 1941 to basically 1950. Well, as it is well known, Le Ray was made a war prisoner, and he spent 5 years in a camp which was called an Offizierlager, which is camp for officers in German, and which was rather mild condition, and there was a kind of home rule in such camps. That means the French officers elected their leaders, and their leaders had to negotiate with the German leader, with the German commander of the camp. So it was kind of home rule, and Le Ray was able to organize a so-called university within the camp, and which was a way to, officers were not forced to work as ordinary soldiers were sometimes forced to work in fields or in factories, but they had to find something to do. Okay, Le Ray organized that. Well, I suppose to have been the French leader in such a situation would have been sometimes a difficult situation, I can imagine. It is known, I know from family witnesses, that the Jews were not usually chased in such camps, except if some Frenchmen pretended that they were Jews and they don't send them to the office. Okay, that's another story. So Le Ray, who was an expert in fluid dynamics, was approached by especially Hasse to work on different projects for the Germans, for instance, to be editor of Centralblatt or maybe to work in the field in fluid dynamics. But then, in order not to be able, he stayed, which was very brave, he stayed in his camp, and developed topology. It's not by chance, because there was already the fixed point theorem of Schauder and Leray, which was already topological in spirit, but which was used to prove uniqueness or existence and uniqueness solution of nonlinear differential equations, especially in fluid dynamics. So what Leray invented this sheaf, and his main motivation was the following. Suppose that you have two topological spaces and a map from the space X to the space Y. Okay. Now, you want to calculate the cohomology of X, and at that time cohomology means check cohomology, the cohomology of X in terms of the cohomology of Y and of the mapping. So basically the idea of Leray was the following. If I take a point Y in this, small y, then I consider the fiber, the pre-image, fiber f minus 1y. I consider the cohomology group of this fiber, and I study how they change when the y moves. Okay. Under reasonable condition, for instance, if it's a locally trivial bundle, then of course it's locally constant, because in a small neighborhood around y, you can identify the fiber with each other and the cohomology with each other. But what happens when you move out? Of course, the idea of a local system was already known. By, I think it's Whitney who introduced this. I still don't know Whitney. I'm not sure. But at least it was known to both. So the idea of local system and other topologies, that you have a system of coefficients which vary from one point to another one. Okay, now you want to reconstruct, you have the new data are that you have for each fiber its cohomology group, and you want to reconstruct the cohomology of the total space out of this information. And that's where Leray invented the so-called spectral sequence, which sometimes is called the Leray causal spectral sequence, for the reason that Leray invented it, but in a specific situation. And causal use it in another situation. He used it for the homology and cohomology of Lie algebras. But then, if causal felt necessary to give a general formulation of what is a spectral sequence, and general sequence, and he gave the solution that it's a collection of complexes, each one being the cohomology of the previous one, which is a very, very good and sometimes misleading presentation. Very good, but sometimes misleading. So this, and then this spectral sequence is something which enables you to reconstruct the cohomology of X from the cohomology of Y and the cohomology of the fiber. And Leray and many other people, developed this idea, and especially Armand Borel, use it to consider the cohomology of groups, because if you have a group and a subgroup, if you have D group H and G, then you have the projection of G over GH, homogeneous space, and it connects the cohomology of G with the cohomology of the subgroup and the cohomology of the homogeneous space. And Borel used this with great, in his thesis with great benefit. Okay, so that was already known, and but Leray did not, well, because of course of the conditions, he published his final account only in 1950. So I will not enter into the je ne peux pas répondre, je ne sais pas. Je pense qu'il avait certainement des exemples en tête, mais je ne pourrais pas. Bon, I think he was motivated by his study in functional analysis before. Okay, so that's what we had. Then the final account was published only in 1950. And then in between, so Armand Borel used immediately, Armand Borel, who was at the time in Zurich at the École Polytechnique, ETH. Montborel used that for common groups, and that remained one of his best contributions. Okay, then in between, then other people joined, and Carton, Henri Carton, studied that already starting from 46, 47. And Carton was invited in Harvard in the beginning of 48, yeah, so beginning of 48. And there is a story that his plane was delayed and he could not be surveyed well, okay, you can write a novel with that. Okay, so, and the daughter of André Weil has written a novel about that. Okay, so Henri Carton, and then Henri Carton had another approach. At this occasion, he developed the idea of a grating, or which is in French, carapace. And I will come back to this idea later, grating. So it was another approach. But then Carton, and you have also to mention André Weil, who enter into the game, and André Weil was obsessed by the theorem of Durham theorems. And he repeatedly said that that's the core of geometry. The Durham theorem is the core of geometry. So, and André Weil published a version of a proof of the theorem of Durham, which is by far the best possible, the best, and which influenced Carton. Of course, André Weil would pretend, I don't know what is a sheaf, it's just a stenography, you would say. Well, that was part of his way of saying. But when you look at his proof, it's clear that he perfectly understood what is a sheaf. Okay, now so there was a period of hesitation, and Carton, when coming back from Harvard in 47, 48, and 48, 49, in his first seminar, in his official seminar, which is available in this collection of books, this collection. Then Carton explained both in his lectures in Harvard and his seminar a way to define sheaves, grating, etc. But he was not happy with that. He was not happy with this. And this part of his seminar has been dropped from the published version of the seminar. And it started again in 1951 in a long seminar, which was in collaboration with Samuel Eilenberg. And it's the first time I attended a mathematics seminar. I was a first-year student at École Normale at the time. And then it started again. He started again to develop this in the last part of his one, and this recorded in this volume. Then he started with a completely new point of view, and then he gave a general definition of sheaves. But mostly under the influence of Michel Lazare, who is credited for that. He developed this idea starting not from the sheaf as collection of a section of open set, but the corresponding étal space. And it's clear that it is it's dominant in its exposition, and so it comes at a variance from the modern exposition. Well, of course, I will come back to that later, to the various views about sheaves. But then it started again, and that's Henri Carton, but he was influenced by Samuel Eilenberg, who gave in the first part of the seminar an account of the homology and cohomology of group in the axiomatic spirits. Of course, Samuel Eilenberg and MacLean invented the cohomology, and other people invented the cohomology of groups, also. But for the first time, Samuel Eilenberg presented it into an axiomatic way. And he gave a series of axioms for the cohomology of group, which could be more or less immediately translated as axiom for the cohomology of spaces. But the point of view is changing. Because so far, when people develop the cohomology of spaces, well, there was Czech, Spaniard, there was Durham. They choose coefficients, a space, and coefficients, they kept the coefficient and let the space vary. For instance, you take cohomology with real coefficient and associated to the various spaces. The point of view of this is a dramatic change of point of view. Now you have one space, but you take the coefficient as variables. That means you consider one space, you consider the category of all sheaves, or coefficient, whatever, over that space, and the cohomology is defined as depending on the coefficient. The space is fixed, but the coefficient vary, which is a totally new point of view, of course. And then we have also to remember that about the same time, for the historical purpose, to make that Heidelberg and Steenrod published in 1951 Foundations of Algebraic Topology, where they gave an axiomatic description of the cohomology group of a space with coefficients which are fixed, not a sheaf, and then they proved that for reasonable category of space comprising all the standard spaces, the cohomology is uniquely defined by this axiom. But one crucial axiom is that the cohomology of a point is trivial. H0 exists, it's a coefficient of the cohomology, H1, H2, etc. are 0. And this was more, but later on, it was, this condition was removed, and the so-called extraordinary cohomology were invented mostly by Quillen and other people, Karen Quillen and so on, to get account of this. So, but it's not the point. So the change of emphasis is the following. The space is there, but it's just the place to put all the sheaves. Okay. Now, about the development. So Henri Cartan, in his seminar, and I spent yesterday evening and reading again this seminar, and so give an axiomatic description, prove a uniqueness, existence and uniqueness theorem, but with some restriction on the space. Is used, well, Henri Cartan was obsessed by the idea of treating cohomology with compact support and cohomology with ordinary support at the same time. So introduce a certain collection, he has a space X, but he introduced a suitable collection of closed subsets of the space, and he considers this the cohomology with support in phi. Phi may be the set of compact subset of a locally compact space, or the open closed subset of a paracompact space. Paracompact spaces are a slight extension of locally spaces, which was invented by Dieudonné in 42 or 43 for the purpose of decomposing a continuous function in two variables as a sum of product of function of one variable. So that makes the exposition slightly disturbing, but the point is that there is a restriction. This restriction on phi forces you, if you want to have general cohomology with a closed support, that the space be paracompact. Well, paracompact, as I say, is a slight extension of locally compact, but an important result is that any metric space is paracompact. Okay, and that was enough for applications, for various applications. But there was a restriction. And soon after that, Serre came as a dog in the garden, twice. First of all, in his thesis, which was defended in 1951, he applied this idea to homotopy problems. So, and the main object was the loop space, or well, the loop path space of if you have a space X, then you consider the space of all paths originating in a given point 0, and you consider this with a proper topology, and you study this is certainly not a locally compact space, and you study the cohomology of that in order to get information on the homotopy of the given space. That is thesis. And with great success, because he had a great success with a homotopy group of spheres, with the hope that we could calculate all the homotopy group of spheres, but we are still far from that, unfortunately. Okay, so Serre came, and he had to, so he needed both cohomology for these new spaces, which were not locally compact, not paracompact, and also he needed these spaces, and he needed the spectral sequence, because the spectral, you can consider the state of path is a vibration over X, over space X, what is called now a Serre vibration, which is characterized by the lifting possibility of lifting of polyhedra. Then you have, but in order to calculate P, the point is that P is a contractible space. So the cohomology of P is nothing, except for one. It's the same cohomology as 1 point. But you want to have information about the homotopy. And homotopy, then you can consider that the loop space is a fiber of this projection. So Leray strategy is to combine the cohomology of a space and the cohomology of the fiber to get the cohomology of the space. That's what it is done, for instance, in Borel. But here, the cohomology of this P is known. It's a contractible space. But so you get an interconnection between X and omega, and the point, well, which gives you information about the homotopy groups. But unfortunately, both the theory of sheaves and the cohomology of sheaves and the notion of fiber bundle did not work. So he had to invent, and he explained to me recently that in his thesis he made a comment, I have to reprove, well, he was cautious about not disturbing Leray, and I had to reprove some statement or make a new connection, etc. And he explained to me that it was quite delicate not to offend Leray, who was not an easy character. Okay, so Sear did that. And obviously one needed, and then he invented ad hoc method. In order to fit with the vibration, he introduced not a singular homology, but not with model which are simplices, but cubes. Now we have much better tools in simplicial homology, and we can deal with using bisimplicial, Heisenberg, Zilber, and so on. We can do this directly, but he was forced to use cubical homology. But he had to prove that cubical homology was the same as simplicial homology. So a lot of discussion, of course, great progress, but at the cost of crossing the boundaries. Now, Sear did cross the boundary a second time, where he used, well, first of all, in between there was the work of Cartan and Serre on complex variables, many complex variables. And then they used sheaf cohomology with great success to deal with problem of many complex, well, holomorphic function of many complex variables, where the topology is quite delicate. A Riemann surface on one variable is rather easy to discard. A Riemann surface in many complex variables is an awful object, which is really not completely understood. Okay, so, but then Cartan and Serre used sheaf cohomology. They did not create a new cohomology. They refer on the Cartan cohomology, which was defined, as I mentioned, first in 46, 47, and in the new form in 50, 51. Okay. But after that, they obtained the so-called theorem A and B, which are famous theorems in the cohomology of coherent sheaves of holomorphic functions. But then Serre developed application to projective spaces, and using a certain trick which was given to him by someone in the group, and then he used sheaf cohomology, but he used for projective space cohomology of projective space, and then he realized that his methods were basically algebraic. But what was needed? What was needed is Zariski topology. By the way, Zariski topology, as we know it today, is not what Zariski invented. He invented a variant of that, a topology on the set of all all valuation rings of a given field, which is not exactly the same, but which was used sometime by other people. Zariski topology. But the Zariski topology, the rumor is that This was invented by Chevalet in a seminar given by Zariski. Well, I have no real proof, but it's it seems quite reasonable to assume that. But the Zariski topology was first used by André Weil. André Weil in 1948 gave a course in Chicago, which has not yet been published. Unfortunately, I tried repeatedly to have it published, but I did not succeed. He gave a course about what are fiber spaces in algebraic geometry. Of course, and then if you have a fiber space, the main property is that it should be locally trivial, but locally trivial means that you need a topology. And from various conditions, it was clear that the good topology was Zariski topology. So it's really André Weil who invented, well, used for the first time seriously, and also he was connected with so-called Cousin problem, which is to reconstruct a meromorphic function in many complex variables out of the set of, or the poles, divisor of the function, and zeros and poles. Okay, so André Weil was the first to insist on the Zariski topology as a tool to imitate topology in algebraic geometry. And then Serre knew that perfectly. Serre wrote a report for the Bourbaki seminar about this work of André Weil. And he immediately tried to imitate what he had done with the help of Cartan for a complex projective space viewed with cohomology of sheaves over complex projective space. And as he explained to me many times, I mean, it was so easy now. It was so easy now. So easy now compared to what he had done with Cartan in complex variables. So it's Serre who invented his famous paper, which was finally published. I don't remember it. Well, it was written in 53, but published in 59, 55. That's Serre. And then I remember my surprise when he presented to me part of his manuscript. An algebraic variety is a topological space with blah, 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 blah. Wow, a topological space in algebra. It was a surprise to many people. Okay, then, but he had to use sheaf cohomology. But Zariski topology is a terrible object compared to ordinary topology. It's completely exotic compared to ordinary topology. And there was no sheaf cohomology available for that. And then he had to reinvent it in a slightly different way. So, Serre twice crossed the borders, showing the necessity of going beyond ordinary spaces and sheaves over ordinary spaces. But this time you had to, the challenge was to invent a cohomology of sheaves without any restriction on the space. At the time, Grothendieck was back to Paris, and we had many exchanges at the time with Grothendieck, and it's Grothendieck who provided the first solution. He provided it in his typical way. First, well, of course, the main challenge was the following. From homological algebra, known method of homological algebra, the book of Cartan and Heidelberg was just printed at the time, appeared just at the time. In order to define cohomology, you need resolution. While if you have a module, for instance, that modules is a quotient of a projective module is easily a quotient of a free module, so you can define a projective resolution quite easily. But dually, injective resolution. At first, injective objects were invented just by duality because Heidelberg was obsessed by the duality. And obsessed. If you take a diagram and reverse all the arrow, what happens? If you define by a diagram the property of being a projective, reverse all the arrow, you have the definition of injective. But it was a quite exotic object, an injective module. And it's not easy to prove that the modules can be embedded in an injective module. Bayer gave a proof which is quite sophisticated. Then, okay, so it was clear that for sheaves, you don't have projective sheaves. You don't have free sheaf, projective sheaves, whatever. You don't have them. So the need is you have to go to the other side and take the injective sheaves. But to construct an injective sheaf was not obvious, and no one knew how to make it. Okay. Then Grothendieck came from the sky. I mean, he said, in order to prove that any object can be embedded into an injective object, I use a Bayer construction, and I look at what are the formal properties used in this proof. And the formal properties are basically, the crucial idea is that if you have a module M and a connection of some module M alpha and another module, it's a distributivity law which is intersection, intersection of M alpha plus N is something, intersection of M alpha plus N, something like that. I'm sorry. Okay. You are right. Yeah, you are right. Okay. Well, one basic ingredient in the proof was this. So Grothendieck invented the idea, come from the sky. I will consider an abstract category, and at this point he invented the notion of abelian category, which was about the same time invented by Buxbaum under the name of exact category. So that was more or less natural, a natural idea. The new idea was to introduce this as an axiom, somewhat corresponding abstract form of this axiom. And then, repeating the Bayer construction, you can prove that any object can be embedded into an injective object in a given category. So now the next step is to prove that for shifts it works. Well, but it's a rather easy exercise. So in this way, Grothendieck could prove from abstract principle that a sheaf can be embedded in an injective sheaf, and then you have injective resolution of sheaves. Okay. But almost immediately, Godemand came with a more explicit solution. Godemand came with almost immediately with an explicit solution, which is the following. Take a sheaf, F, over a space X. Now I consider the various fiber, Fx, for all small x into X. And take the product of the Fx, which amounts to the same. You have X a space, and you have X delta, which is the same space with a discrete topology. You have a natural map, of course, natural map, which is continuous in the right direction, call it pi, and then you play with the factor pi star and pi over star of direct image and inverse image. But for this map from X delta to X. And then it's easy to show, when you have a discrete space, what is a sheaf over a discrete space which is injective? Each fiber is injective. So it was easy. So that's a solution that was provided by Godemand, and he had various forms of these conditions, slightly various forms. So here we are. Grothendieck invented, by his new categorical theory of abelian category, he is able to prove that you have injective. You can apply it to the shift. You have injective shift. You can repeat exactly word for word what was given in the Cartan and Lebert for modules and get in one or two pages all the necessary properties. Okay. And then, as I said, Godemand in his textbook repeated that with a slight variant of that. Okay. So now, we are, I checked yesterday that Godemand book was published in 1958. Now, the famous paper of Grothendieck, which is called Talk, because it was published in the Talk Mathematical Journal, was written in 1955, and copies were circulated and discussed among Bourbaki at the time, but it was published only in 1958. So the book of Godemand and Grothendieck papers appear at the same time, and they refer to what Godemand refers to Grothendieck, of course. Okay, so that's now what we have. At the moment, you have now a completely general theory of sheaves and sheaf cohomology over an arbitrary space, and you can cover both the point of view of Serre. I mean, the Serre vibration is, and the path space is covered by this new theory, and also the application to algebraic geometry. So that's what it was around 1958. Now, combien j'ai encore de temps? Oui. Ouais. Non, 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 non. Non, 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 non. Non, elle était connue. Check homology was known, but it was no, 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 no. Carton gives us for certain spaces the homology is a check homology, and already Leray had theorems comparing his homology with check homology. Spanier, singular, and what was the last one? Spanier, singular, and Durham. So we had already many. Oui. Oui. Ah. Oui. Oui. No, but already, well, Leray already compared. Well, Leray defined check homology for sheaves and compare it with his homology. And under suitable condition, it's the same. Okay. Pardon? Si. Leray invented the chief homology. No problem. And then Carton gave another version, but it was, or well, another presentation, I would say. But no. He doesn't define it as check homology. No, he defined it in general. And then he proved that by resolution. I will come to that at the last moment. Okay. So that's exactly the idea of grading. So, okay. So at that time, since that, what we had, of course, what became very important and what precedes Topos is that first of all, there is a comparison between, the comparison between the 2 points of view. It's either a étal space or it's a collection of sections over the open. In Carton's seminar, it takes a definition for étal space, gives one, in a few sentences, he says, we could also use it in this way. But I think Carton was dealing with complex variable, and he was influenced by the point of view of Weierstrass. Okay, so, yes. But the notion of pre-sheaf, for instance, which is so familiar today, doesn't appear explicitly in either case. So, of course, there are some remarks. If you start with what we call now a pre-sheaf, you can generate, etc. But usually what was done is that when you had a pre-sheaf, you associated to it an étal space, and étal space was considered a sheaf. But the problem of sheafification, starting from a pre-sheaf to get a sheaf, was not really, present in this day. It's really Grothendieck who introduced it in his SGA4, this point of view, for more general situation. So, another problem is about a continuous map F. So, if you have a sheaf as here, you can define an inverse image F star G, which is F star G, which is here, and you can define a direct image F star F there, and then there is these two factors are adjoint to each other in a proper way. And by the way, when the adjointness is not as mentioned in both Carton and Baudemont is not the right one. They take a right adjoint instead of a left adjoint, etc. So, but then this was not realized as such importance. But now, of course, the point is that if you want to define the direct image, is very easy using the definition of a sheaf as collection of section of open sets. Because the section of this over space U is simply F of F1, V, F minus 1. But the inverse image is better using the ether space. Okay. So it shows that you have to do with both. Now, so there was this problem, and it was important that when you have a continuous map from X into Y, you have two functors for sheaf, one which is inverse image and other one direct image, and they are joined to each other in the proper way. And the existence of this adjointness is crucially considered as a crucial property by Grothendieck. The new idea of Grothendieck is to replace the space X by its collection of sheaves, by its category of sheaves. And now instead of having a continuous map from X to Y, you replace X by its topos, which is its category of sheaves, Y by its topos, so-called X, the topos. These are now categories. And then instead of having F, you have two functors, F lower star and F upper star, which are joined to each other with suitable property. So that gave the definition of maps between what we call geometric functors between toposes. Then there was another important fact, which is when you have a pre-sheaf. And as I said, a pre-sheaf is what? It's just a functor. Well, in modern terms, you have a space X. You have the category, let's call it TX, topology of X, which is a collection of open sets. So that's the object of this category. And the map is just simply the inclusion. If U is in V, you have an injection of inclusion in U of V, and that's only maps which exist. So this, and now a functor, contravariant functor from TX to, let's say, category of set, category of rings, category of whatever, category of cows if you want to have sheaves of cows. And then it's a covariant, so it's a functor TX up to, let's say, sets, if you want to also see. Okay. Then how can you generate a sheaf? The idea is the following: in Godemont, Carton, etc. The idea is that first with such a functor you associate a space E, which is étal over X, and then you take the section of this space to generate a sheaf. But the disadvantage is that you have to use the point of your spaces. And it's contrary, it's opposite to the spirit of categories. The spirit of category, you should never mention, rarely mention the point of a set or a space, but only what maps, etc. So this was not very satisfying. And as a result, it's not very mentioned. It's Grothendieck who really understood the importance of it. And the point, what is important is the sheafification, which is so-called pre-sheaf. Pre-sheaves are just, the collection of these contravariant factors with no relation. And then you have sheaves, which are which are, of course, a special class of pre-sheaf. Now you have the inclusion map. A pre-sheaf is a pre-sheaf. And upon the sheafification, a sheafification functor is, well, here you have the injection of this category into this category, and there is an adjoint. Which is, call it S, an adjoint, with suitable properties. The point is that an adjoint of a functor satisfies automatically certain conditions with respect to limits, and you put another limit. So co-limits, general co-limits are preserved by S, but you have to assume a little more. So now the point, what was really important for Grothendieck is realizing the analogy between these two situations. First of all, if you replace the space by the topos of all these sheaves, then a map corresponds to a collection of data of two adjoint functors. And again here, but it's completely different. You have a sheaf, you have the category of pre-sheaf, and you have a subcategory, and again two adjoint functors. And this is really the crucial discovery of Grothendieck in this case. And then starting from these two examples, you can formulate the general definition of a sheaf, which is a topos. Well, elementary topos if you want, but these are special case, usually called Grothendieck topos, which are a particular case of the elementary toposes. Okay, so I just finished that, and so that's a rather short historical account. The last part should be much more developed but then we are very close to Grothendieck, or already in Grothendieck. So I wanted to describe the prehistory, the prehistory, the prehistory, and then, the history begins there. And it's a different story. I just wanted to show you that the notion of sheaves was natural after Riemann and Weierstrass, the 2 points of view. Then it was developed in the 40s and 50s by especially Leray, Cartan, Borel, and Serre. That's the people who should mention. And then after that, after this big synthesis, both by Cartan and by Godemain, then it started. But of course, sheaves have many other applications which I did not mention. For instance, microlocal theory of sheaves, perverse sheaves. So I don't have time to develop all this, the development of sheaves. I just wanted to retell the creation of sheaves. Thank you very much.